Hey everyone, ready to dive into some seriously cool science?
Always.
Awesome. Today we're going to be talking about some research from Princeton that's really caught our eye. You know how we're always talking about plastic waste and the environment?
Yeah.
Well, these scientists may have just cracked the code on a plastic that's not only super flexible and strong, but get this, also recyclable.
Oh, yeah. This is a big one. And easy to make, too.
Exactly. We're talking game-changing applications here. Think custom shoe soles, flexible robots.
Medical devices. The possibilities are pretty wild.
Totally. So let's get right to it. The article that sparked this deep dive is called Stretchable, Flexible, Recyclable. Princeton scientists developed fantastic new material. It was published just a couple of days ago, December 29th, 2024, on the Princeton University website.
Right. And the really cool thing is they're not using some rare, expensive material here.
Yeah, the article mentioned something about thermoplastic elastomers, right?
Exactly.
So break that down for us. What exactly are those?
Well, you know polymers, like the building blocks of most plastics.
Uh-huh.
Thermoplastic elastomers are a type of polymer, specifically a block copolymer.
Okay, and remind me, what's special about block copolymers?
Think of it like Legos. You've got different blocks, like different sets of Legos, all connected together to make a bigger structure.
Okay, I'm picturing it.
But each block still keeps its own unique properties. Like you can still tell the difference between the red Legos and the blue Legos, even when they're all snapped together.
Right.
So in these thermoplastic elastomers, you have different blocks that behave differently, kind of like oil and water. They don't really want to mix.
Gotcha. So that's how they get that combination of, like, strength and flexibility.
Exactly. But here's where things get really mind-blowing. They've managed to create these tiny, stiff structures within the block copolymers.
Tiny how?
We're talking nanometers here. Like, a human hair is thousands of times thicker.
Wow, okay, that's seriously tiny.
Yeah, and these stiff structures are like little cylinders embedded within the stretchy polymer matrix. So it's like having rigid rods inside a flexible material.
Yeah. So they're getting the best of both worlds, strength and flexibility, all in one material.
Exactly. And they can control all of this using 3D printing.
Ah, okay, so that's how they build this stuff.
Yeah.
3D printing.
Yep. They can actually arrange these tiny structures as they build the material, layer by layer.
So they can customize the stiffness and flexibility in different parts of the object.
Precisely.
So, like, imagine a shoe sole that's stiff under the heel for support, but flexible in the front for comfort.
Exactly. That level of customization is what makes this so groundbreaking.
That's wild. Okay, so there was also something in the article about thermal annealing, right? What's that all about?
So thermal annealing is basically just a fancy way of saying they're heating and cooling the material in a very controlled way.
Okay, and why do they do that?
Well, it actually serves two really important purposes.
Okay, hit me with number one.
First, it makes the material way stronger after it's been printed.
Okay, makes sense. What's the second reason?
This is the really cool part. Thermal annealing also makes the material reusable.
Reusable?
Mm-hmm.
Okay, so you can, like, melt it down and reshape it.
Sort of. But it gets even better than that. It actually allows the material to self-heal.
Wait, what? Self-heal?
Yeah, you heard that right. If the material gets cut or cracked, you can apply heat, and those molecular bonds, remember those Legos we were talking about?
Yeah?
They'll actually reform, basically stitching the material back together.
No way. Seriously.
Silly.
Okay, so we've got super flexible, super strong, self-healing plastic. And then on top of all that, the article mentioned that they made the plastic glow red under UV light.
Yeah, they added a special organic molecule to do that.
An organic molecule, huh? So is that, like, really expensive or something?
Actually, no, not at all.
Okay.
And that's one of the most exciting things about this whole process. It's super cost effective.
So how cost effective are we talking?
Like about a cent per gram.
Wow, that's crazy. So not only is this method super innovative, but it's also really affordable.
Right. Which means it's got huge potential for all kinds of real-world applications.
This is mind-blowing. It feels like we're on the verge of a materials revolution.
I think we are. And
Yeah.
the coolest thing is, this is really just the beginning.
So before we get too far ahead of ourselves, let's take a closer look at this whole self-healing thing. How does that actually work at a molecular level?
And that's why this material is so fascinating. I mean, we're not just talking about some cool new plastic. We're talking about a potential solution to this huge plastic waste problem we have.
Totally. So let's dive a little deeper into that self-healing magic. What's actually happening at the molecular level?
Remember those stiff, cylindrical nanostructures we were talking about?
Uh-huh.
They're actually held together by these weak molecular bonds. And so when the material gets damaged, these bonds break.
Okay.
But here's the thing. When you apply heat during that annealing process, those bonds get enough energy to reconnect. It's like they're stitching the material back together, but at a microscopic level.
So it's like the heat is acting as like a molecular glue.
Exactly.
And the coolest part is that it can like reheal multiple times, right?
Yep.
Without losing its strength and flexibility.
Exactly. That's why it's so durable and sustainable.
It's wild. I mean, think about all the stuff we throw away just because it gets a little crack or a tear. This could totally change that.
Absolutely. It really opens up some exciting possibilities for a circular economy, where materials are reused and recycled instead of just ending up in landfills.
Definitely. And speaking of exciting possibilities, you mentioned earlier that they were able to make the plastic glow in the dark using, what was it, an organic molecule?
Yeah.
So are there other things, other functionalities you could add to this material?
Oh, the potential is huge. I mean, you could imagine incorporating conductive materials to create like flexible electronics or sensors that react to temperature or pressure changes. You could even create materials that release medication for medical applications.
Whoa. Okay, that's getting a little sci-fi. So we're talking flexible electronics, smart sensors, maybe even like medical implants.
All of that and more.
It sounds like we've only just scratched the surface here.
Definitely. The ability to really tweak materials at the nanoscale unlocks so many opportunities for innovation. It's like having this massive toolbox of building blocks that you can combine in tons of ways to create totally new materials with completely new properties.
It's pretty mind-blowing. And it's not just theory, right? I mean, the article talked about how they printed that tiny vase and the word Princeton using this technology.
Right, and that really highlights how precise this 3D printing technique is. I mean, they were able to create some seriously fine details.
And they did all of this using a pretty standard 3D printer, right? Which is huge because it means this technology could be adopted by like different industries and even smaller companies without breaking the bank.
Exactly. It has the potential to democratize access to these advanced materials and manufacturing techniques.
That's a game changer. But I mean, surely there are some challenges here too, right? What are some of the hurdles that researchers still need to overcome?
Well, one big one is figuring out how to scale up production. I mean, the material itself is cheap, but optimizing the printing process for mass production, that's going to take some more research and development.
Right. And I'm guessing there are like limits on the size and complexity of the things you can print with this technology.
For sure. Right now, it's best suited for smaller objects, creating larger, more intricate structures while keeping those desirable material properties. That's definitely something that still needs a lot more research.
It sounds like there's a lot of exciting research still to come.
Definitely. This field is constantly evolving. We're constantly pushing the boundaries of what's possible with materials science.
This has been an awesome deep dive so far. I mean, from the microscopic level all the way to these real-world applications, it's really incredible to see how this new material could revolutionize so many things. But before we get ahead of ourselves, let's zoom out for a second and consider the bigger picture. What could this technology mean for our world in the next 5 to 10 years? I mean, it really does feel like we're on the cusp of something huge here.
Yeah.
This isn't just about, like, a cool new plastic.
Right.
It's about, like, totally rethinking the way we design and manufacture and use materials in our everyday lives.
Absolutely.
So let's imagine we fast forward like 5, 10 years down the line.
Okay.
Where do you see this technology having the biggest impact?
Oh, I think we're going to see this being used in just about every industry you can imagine. I mean, healthcare, robotics, consumer goods, even aerospace.
Whoa. Okay, break that down a little.
Sure. So imagine lightweight, flexible prosthetics that are custom designed for each person.
Yeah.
Or drones that can withstand collisions and repair themselves.
That's wild. And it's not just about the fancy high-tech stuff. I mean, I could totally see this changing the game for everyday things.
Oh, absolutely.
Like footwear, athletic wear, protective gear.
For sure. I mean, imagine shoes that adapt to your foot shape and provide personalized support.
Okay.
Or helmets that are both lightweight and incredibly impact resistant.
That would be awesome. And then, of course, there's the whole environmental impact.
Right.
We were talking earlier about how this material is recyclable and self-healing. So could this actually help us reduce plastic waste on a larger scale?
I think it absolutely could.
Yeah.
I mean, think about it. Products would last much longer
Right.
because you wouldn't need to replace them as often.
And we could potentially start using bio-based polymers.
Exactly.
So we could move toward these like truly sustainable materials that break down naturally
Right.
and don't pollute the planet.
Exactly.
It's kind of crazy to think that plastic could actually become like a valuable resource
Yeah.
that we can reuse and repurpose.
It's definitely a shift in perspective.
Yeah, for sure. It feels like this discovery is a huge step in the right direction.
It really is. It shows what we can do when we combine scientific innovation with like a real focus on sustainability.
Totally. It's a testament to like human ingenuity
Mm-hmm.
and our ability to find solutions to these huge challenges we're facing.
Yeah, and the most exciting thing is we're just scratching the surface.
So as we wrap up our deep dive into this remarkable new material,
Mm-hmm.
what's the one key takeaway you want our listeners to walk away with?
I think the biggest thing is this. The future of materials science is all about precision and customization.
Okay.
We're moving away from this like one-size-fits-all approach
Yeah.
to materials that are tailored for specific applications and even like individual needs.
It's kind of like we're moving towards materials that are like smart,
Yeah.
responsive,
Mm-hmm.
adaptable,
Exactly.
almost like living organisms in a way.
Yeah. And as we, keep exploring these possibilities with nanoscale engineering and 3D printing and functional additives, I think we're going to see even more groundbreaking discoveries in the years to come.
Well, that is an amazing note to end on. A huge thank you to everyone for joining us on this deep dive into the fascinating world of new materials. Until next time, keep exploring, keep learning, and keep those imaginations running wild.